What is an algorithm? That's a strange word you hear a lot nowadays. The word comes from distorting the name of a mathematician from ancient Persia, Al-Khwarizmi. But what does algorithm mean exactly? Please pause the video and say in one sentence, in your own words, what an algorithm is. Go on, I'll wait. Stop now. Welcome to Stajano Explains. I'm a professor in the Department of the Science and Technology of Computers at the University of Cambridge, where, among other things, I teach a first-year course on algorithms. So if you want to find out about algorithms, you've come to the right place. This is the very first video of that course. According to the statutes and ordinances of the University of Cambridge, I own the copyright and performance rights over my lectures, so I can do whatever I want with them, and I have decided to put them here on my channel to inspire and guide not just my own undergraduate students at Cambridge, but also anyone else around the world who wants to become a better computer scientist. Whether you're studying for a degree at another university, whether you're still at school and figuring out what to do next, or whether you are already employed as a developer and you want to improve, which, by the way, is a wonderful thing to want to do. So feel free to browse around. There's plenty of material, and I put out a new video every week. You're getting exactly the same lectures as my Cambridge students. If you benefit from my free teaching materials, a cheap way for you to say thank you is to hit the like button on these videos so that the YouTube algorithm will get a hint and offer them to other people who might enjoy them. With that said, what did you say an algorithm was? I would say an algorithm is a systematic recipe to solve a well-defined problem in a finite time. I'm not implying that what I just said is the only sensible way to define algorithm, but I would emphasize systematic recipe above all else. Is this close to what you said? Usually when we talk of an algorithm, we talk of something a computer will execute, but it doesn't have to be so. You could describe an algorithm for choosing what to eat for lunch, or for determining which house to buy, or for riding a bicycle without bumping into pedestrians, or anything else. But in this course, we will stick primarily with algorithms that are meant to be executed by computers. Now, when I say systematic recipe, I mean I'll be very thorough when I describe exactly what happens in every possible case, so that my recipe works even if it's applied mechanically by a machine that is totally devoid of common sense, as computers are. If something unexpected happens, you or I might naturally adjust the recipe, but the machine won't, and it will trip over if it comes across a step it cannot execute. So you have to be very precise and think ahead of all possible situations. Actually, most programming is quite mundane. Much of the code the typical programmer writes is not that hard. It mostly just moves data around. However, in this course, we will see some core programming gems that are pretty clever, maybe just a couple dozen lines, but truly ingenious. And once you understand them, you wish you had come up with that kind of stuff. So these bits of cleverness are so useful, and yet so easy to get wrong in subtle ways, that they tend to be written and debugged properly once and for all, and then packaged up for use in some standard library. And in this course, we study this kind of uncommonly ingenious programming exploits, clever approaches for solving problems by computer. And don't be distracted by the fact that usually in your professional life, you won't have to write them yourself because they already exist in the library, in some library. So this is the course in which you acquire the core computer science skills that would allow you to write the library, perhaps for a radically new computing environment that your startup is creating or something like that. So if you are here, you've probably already done some programming, and if I offer you an exercise, you might say, oh, well, for this particular problem, I might use a hash map from the Java collections library. But no, that would be missing the point. You should imagine you only have plain memory at your disposal. No prepackaged hash maps or array lists or any other fancy things. You have to build all your data structures from zero yourself, ideally in machine code being the only language that the processor natively understands, or at best in C, which we might consider a polite version of machine code, and without relying on libraries written by others. You're not a serious programmer until you can dominate recursive data structures with lots of crisscrossing pointers and make them behave as they should, as you want them to behave. And when you finally remove the last bug from that kind of complex code, and it works, then the satisfaction of that moment is priceless. Algorithms and data structures are truly the core of computer science. Obviously, you can't do any programming without using algorithms. They are a foundational topic, not just for this particular course, but for practically every other course in the computer science tribus, and indeed for almost anything else you do in your computer science career. If you are going to be a competent computer scientist, it's important that you understand algorithms and data structures in depth, not just superficially. An algorithm is correct if and only if, for every instance of the problem, it terminates and it gives the correct answer. So how do you come up with a correct algorithm? Can you do that already? Well, let's try. I'm going to describe 3 problems to you. If you want to get good at algorithms, try solving these problems yourself as seriously as if they were exam questions and your grades for this course depended on your answers. Think about what algorithm will solve this problem, what data structure you should employ. Write down your idea on paper so that you can review and critique it later, perhaps in a month or 2. And in this lecture course, I will eventually teach you how to solve these problems, but you will learn a lot more if you thought about them on your own before being shown a solution. And I encourage you to revisit this video after completing this course, redo the problems with your newly acquired knowledge, and compare your new solutions with the ones you came up at the beginning of the course. So our first problem involves DNA sequences. You deal with strings containing the letters A, C, G, and D, which represent, as you know, the basis of the genetic code. These strings can be very long. Given 2 of these strings, you want to find out how similar they are. You do that to figure out if 2 organisms are genetically related and to what extent. So let's define a subsequence of a sequence of letters, and it is simply the letters of the sequence taken in order with 0 or more left out. Imagine you have 2 strings, and we define the degree of similarity between those strings to be the length of the longest subsequence that they have in common. For example, AC is obviously a subsequence of both of these strings, but maybe it's not the longest. Maybe there are longer subsequences than AC. You can try eyeballing for a longer subsequence, but even if you find one, how can you be sure that you found the longest possible one? Well, to make sure you don't miss anything out, you could try all possible subsequences of the first string and all possible subsequences of the second string and then compare them pairwise. Well, that's fine. It's a systematic recipe, and in that sense, it's an algorithm as I defined it, and it will eventually terminate with the correct answer. But how long will this algorithm take? Well, how many subsequences are there for each of these 2 strings? Try and figure that out. It's not difficult. Then, how many pairs do they form? And how long will it take me to check each of these pairs if your inputs, instead of being around 20 characters long, are in fact millions of characters long? Well, if your very fast computer could check a pair of strings for equality in just a nanosecond, which is probably faster than your computer can actually do, would it terminate before you take the exam for this course in June? Well, try and have a little calculation to see how long it would take approximately, and maybe you'll be surprised. Well, can you find a faster way of solving our problem? Our second problem is what I'll call bestseller chart. Imagine you have a large online store whose catalog lists millions of items. Customers buy items 24 hours a day, there's lots of transactions per second, and the store wants to have a web page with the top 100 best-selling items. There's 100 items that sold the most historically from -infinity to now. And he wants an up-to-the-second list of the 100 best-selling items. Clearly, a trivial way of doing that would be to take the millions of items, each associated with the number of times that it had been sold, and then sort these items using that as the key. And every second you resort the millions of items, you take the top 100 and you throw away the rest. This clearly produces the correct result. Once again, it's a valid algorithm according to our definition. But it feels there's a lot of waste because you also sorted all the millions of items that you ended up throwing away. And will you always be able to finish this operation before the next refresh of the page? What if your boss now wants the page to be refreshed every millisecond? Or what if the catalog grows to billions of items? Will your algorithm still be able to complete on time? Or is there perhaps a less wasteful way of doing it that would go substantially faster and would scale better with the demands of the site as it grows? The third problem I'll challenge you with is database indexing. This time, let's imagine an auction site where people bid to buy items. And each one of these transactions is recorded somewhere in some database. Now, within the auction site, it's reasonable to imagine that there will be some business logic that wants to walk through the transactions sorted by seller, for example. Or maybe wants to walk through the same transaction sorted by buyer, or maybe sorted by date, or sorted by price, or whatever. And you don't really want to resort all the billions of transactions every time you switch from one of these views to the next, because you might want to go back and forth without having to redo all the work from zero. So you might conceivably build and maintain some data structure to help with that, an index by seller, another index by price, and so forth. And how would such an index work? How would you build it? How would it scale when the data structure grows very large? How would it be kept up to date when new bids are placed and new transactions are added to the database that you must also index, of course, across each of these dimensions, seller, buyer, and price, and date, and so on and so on. And would your method still work if some of these transactions got deleted? Would you need to take any precautions to ensure that everything still works as intended? Well, think seriously about these three problems. Try to find your own way of solving them based on what you already know today. And during future lectures in this course, we will study ingenious ways of addressing each of these problems. As these examples show, for each problem we want a specific recipe and often also a specific data structure to go with it, and also we want the algorithm to terminate in a reasonable time for realistically sized inputs. For small toy inputs, even a very inefficient algorithm will do, provided it's correct. But for large-scale inputs, performance also matters. So, first of all, how do we convince ourselves that the recipe we produced is correct? Can we just try all inputs? Usually no, even for a computationally trivial task, such as checking that the integer multiplication algorithm that you learn in primary school has been correctly implemented on the computer. If you were to try all possible pairs of 64-bit integers, you'd be there trying for longer than the age of the universe. It's not enough just to have something that seems to work on a few generic instances that you tried. It has to work for every valid input. And then, as we see from our examples, how long does the algorithm take to run? And I can dig deeper in here. How long does it take to run usually? How long does it take to run when I'm lucky? And conversely, how long does it take to run when I'm very unlucky? Because I want to make sure that it's never going to exceed the resources that I'm giving it. And by the way, what other resources does the algorithm use besides the time it takes to run? Maybe how much memory it uses up, how much disk space, how much network bandwidth, how much energy does it consume? Think of all the other resources besides time that a running algorithm might be consuming. Your job, professionally, might be to compare and choose between several algorithms that are all correct, and how do you decide which one is best? Well, you would have to judge them on some of these other criteria, some of these other dimensions. Correctness is almost always the most important criterion, because you're not going to be very impressed that the program gives you the answer very quickly if it's giving you the wrong answer. But even that is not always the case. There are exceptions even to this rule. For example, when finding the truly correct answer takes unbearably long, but there is a heuristic algorithm which is able to give a decent approximation to the correct answer much more quickly. But anyway, let's not get too sidetracked into that. Usually, correctness is a fundamental property that you require of your algorithm. So, what are my goals for this course? They're pretty ambitious goals. By the end, if you do your part and you actively engage with this material, then you will have acquired some abilities to solve new problems. And in particular, you'll be able to come up with a correct solution to the problem, to come up with a reasonably efficient solution to the problem. You're going to be able to convince yourself and others that the solution is indeed correct. You'll be able to analyze how efficient it is, to figure out whether there are margins for improvement, and if a more efficient solution also exists, you'll be able to assess whether it's worth putting in the extra effort of implementing the more efficient solution, given the size of problems that you expect to have to solve, because sometimes a better solution exists. It's actually not worth pursuing. And how will I teach you to do all that? Well, I'm afraid there isn't a universally applicable meta-algorithm, let's call it, on how to design a suitable algorithm given an arbitrary problem. So I can't teach you that. It doesn't exist. What I'll do instead is I'll show you the classics, the literature of this subject. I will expose you to abstract problems that typically have been distilled by generalizing from real-world problems, and I'll expose you to a variety of techniques that have been developed to solve these problems in the general case. And we'll see the smart ideas that were devised in the past, and you will build a mental toolkit, a library of solutions that have very general applicability. And much of the time, when you then encounter a new problem, some of the techniques in this toolkit, some of the things that I've shown you in the abstract will be appropriate for solving your practical problem. Or maybe the new problem will be at least close enough to an old one that you might adapt a known technique with only minor variations. We said an algorithm is like a recipe, so I'll basically show you a bunch of classic recipes from a good cookbook. Usually when you have to cook some new food you've never seen before, one of those classic recipes that you know can serve as an inspiration, or at least as a reasonable starting point. And this is the cookbook that we are going to be using. This is Corman, Leiserson, Rivest, and Stein, Introduction to Algorithms, 4th edition. It's an excellent textbook, and at some point this was the most cited book in computer science, and it has sold over 1 million copies. It's rigorous, but it's quite readable, and this 4th edition just came out in 2002, and it was several years in the making. I adopted it for my algorithms course at Cambridge Sight Unseen, having taught this course for many years already based on the second and third edition. I had a very interesting chat with the first author, Professor Coleman, just at the time that this latest edition came out. Get yourself a copy of the book, study thoroughly, write your notes in the margin. I know that some of you who competed in informatics Olympiads have already studied on this book even before coming to Cambridge, and well done to you. To a first approximation, every serious computer science has a well-thumbed copy of this book on their bookshelf. And there's a reason for you to want to be part of that club. This is not the kind of book that you use to prepare just this one exam and then resell to another student and move on. It's the type of book that if you are serious about computer science, it will accompany you throughout your career. So don't just buy the textbook and then put it on your bookshelf and feel good about it. You should use the textbook, read it, annotate it in the margin, as I said, with the things that you can't understand, and then later annotate it again with the insights you get once you finally understand. Find the mistakes. Report the mistakes to the authors. There will be some mistakes. And your highest chance for being the first to report a mistake is now that the book is still near. If you're the first to report a mistake, you'll be mentioned on the website for the book. And even if you're just reporting a typo, it will be a thrill to see your name up there. But if you are attentive enough that you are able to be the first to find and report a serious error, an intellectually meaningful error, then you can really pat yourself on the back. And maybe you can even put that as an extra line in your CV. If I were an employer selecting candidates who just completed a bachelor's degree in computer science, surely if someone said, I found class A, a serious error in the Coleman textbook, surely this small detail would make you stand out from the others from me. Now, how can you get the most out of this course? By putting the theory into practice. If you just listen to the lectures, stuff will come in one ear and go out the other. You cannot become good at algorithms without writing a lot of code yourself. First, you must understand the ideas, and that you can do in the lecture and by studying textbook, that's all right. But then you have to write code to implement those ideas and understand why the code you write doesn't behave as you thought and debug it. And only by going through this process yourself will you acquire any competence about algorithms. You cannot learn to play the piano just by watching someone's piano lectures or by studying a piano textbook, even if it's the lectures or the textbook of the best pianist in the world. To become really good, you also must practice on your own several hours a day and commit to doing that for years. And that's the same for computing, that's the same for kendo, which I practice. It's indeed for any activity that you want to become seriously good at. You have to do it yourself. You can't just listen to someone explaining. And as far as this course goes, don't try to memorize stuff in the lectures, rules or formula, whatever, in order to later answer exam questions. You really need to understand the material, and the only way to understand it fully is to recreate it yourself and write a program to implement each of the concepts that we study together, and then debug your program until it works. And that is the path to mastery and self-satisfaction. You might think that the main role of the professor in a university course is to explain the material clearly. Well, I don't. I mean, of course, I think that explaining the material clearly is part of what I should do, but I don't think that that should be my main goal. I believe my main goal is instead to make things sufficiently interesting for you that you will want to go back home, open your editor and start coding them on your own. If you tell me in the comments of this video or of any other video in this lecture course that, hey, I watched your video and you made me want to write some code to implement this and I did it and I finally got it to work, then I'll be really delighted, especially if you're not even my student at Cambridge, but a random enterprising person across the internet. You'll make me feel that I have succeeded in my role as an educator, which, in my view, is primarily inspiring you, because learning only happens with your contribution, with your involvement, with your commitment. And of course, if you do that, you will have your own reward by extracting a lot more value from these lectures compared to someone who just listens passively. If you have a question about the content of the course, if anything I say is unclear, if you think I made a mistake, and I make plenty, let me assure you, then feel free to ask me in the comments. Anything that's relevant and potentially helpful to others, I'll reply publicly for everyone's benefit. Unless you try to be obnoxious on purpose, there really are no stupid questions. You can ask anything. If you pay attention to the lecture and you still can't understand it, it's probably my fault, not yours. And I'll do my best to clarify what I meant in my response to your comment. If you're shy about posting a question with your real name, feel free to create a fake throwaway pseudonymic account just to ask the question. I don't mind. If you're my student on the Cambridge Computer Science Tripos, you may also email me privately from your Cambridge address if you prefer, and I'll treat those questions with high priority. Personally, I prefer public questions here in the comments so that I can give public answers and everybody can benefit from them even months and years from now. But feel free to choose whatever suits you. But please, if you do post a public question on YouTube, then don't delete it after you get a reply, as some people do and have done, because that's really annoying and disrespectful towards the person who took the trouble to respond, whether it's me or anyone else. In our next video in this lecture course, we'll get started with some simple algorithms that will give us an excuse to talk about how to reason about algorithms. And here is also another video that people seem to like, not officially part of this algorithms course, that tells you how to become good at solving programming problems. Thank you very much for watching, and if you want me to rejoice in the fact that you stayed with me till the end, then please say 48-inch monitor in your comment. Happy hacking and see you next time.